Hello and welcome to the first lecture of solid-state chemistry, which is going to be concerned with conductivity in solids. So, as we were discussing, this thing is going to be completely asynchronous, so I will deliver you the content of the lecture, and then in the plenary sessions we are going to discuss some additional content, questions, doubts, and anything else. What is the plan for lecture 1? We are going to first go through the general introduction to the field of solid-state chemistry, and then we are going to go into how bonding actually works when you have a solid material instead of having just a general molecule. Then we are going to move on into electrons in solids. So where do you actually place the electrons? How do they behave? How does this reflect into different conductivities that can exist in solids? And then the final part is going to be about semiconductors, the different types of semiconductors that we can actually have, and how do you transition between the different types of conductivities that you can possibly have. These are 3 different videos, so they're going to be in slots. You need to watch them all. You need to watch them in order, but you don't have to watch them all at the same time. You can feel free to stop at whichever point, take your time, go and take a coffee, take a break, take some notes and everything. If you want to know where we are in the lecture, in the progress, there is a bar at the top of every slide, which is going to change color as we progress through the various topics, so you can see how far off we are in the business. This whole lecture presentation with all the slides is published in Canvas. It's in a feedback fluid document, so the document is interactive. You can download the slides if you want, but you can also have it open to the side of this presentation, so you can actually pinpoint specific questions as a comment on a specific slide. This can help you to remember where you're having doubts. Everyone can see it, so other people that might have grasped this thing differently from you or might also have the same question should also feel free to reply, and we'll keep the thread going. We might use it as an inspiration to see where the most of the questions focus for when we go into the Q&A. So let's go into the first lecture. Now, you enrolled in solid-state chemistry, possibly just because of what was written in the blurb in the course manual, or possibly just because you wanted to take some more chemistry. But solid-state chemistry is inherently something that matches very well with the idea of we like interdisciplinary things, because solid-state chemistry is a subject that in reality is connected to physics, part of biology stuff, some part of biophysics, some part of crystallography, and then there is the engineering part, and the people that work in amorphous materials, the people that work in optics. Fundamentally, everyone that at some point is going to need a material to do their bidding, to do some work, to expect some properties, is going to have some declination of application of solid-state chemistry. So we particularly like it, and you might find it all over the place. So since you can find it all over the place, we are going to discuss through the course where can you very, very often encounter solid-state chemistry without realizing, and figure out how can this thing actually work and why does it actually work. So you should be able at some point to actually interconnect all these disciplines on the basis of fundamental and share the basics that underline all of the disciplines. So why do we actually have this kind of distinction between the different chemistry? Basically, there is the molecular chemistry that is mostly concerned with small molecules. So you have a handful of atoms with some very specific interconnections. You might have to take a long time trying to make this, figure out what is the arrangement, figure out what are the properties, but fundamentally speaking, you're talking about something small on the scale of a few atoms and the length of the bond of some atoms. Now, this can be already blown up when you actually look into macromolecules, which might be enzymes, might be proteins, might be something with like severe level of chains of atoms. So anything that becomes a polymer, so a chain of several atoms that then need to be rearranged in space, then already falls into the macromolecular field, in which each of these ribbons will have a series of atoms. The atoms are interacting, and then the cluster of ribbons are interacting with each other. The complexity goes up, and the capability of this thing is inherently different from the capability of this one. But then we land into materials chemistry and solid state chemistry, and you are in a completely different business in which you cannot isolate a simple cluster of atoms to work with. You need to work with the entire material. So here you can see a very nice cover of the Journal of Materials Chemistry C, in which it really gives you the idea of, like, this is just a rendering, but it keeps the idea of you look at a specific point in a material and you see stuff that goes on and on and on in 3 dimensions, infinitely repeating, and you cannot say, oh, but I just want to look at this region. If you want to look at the material, you need to go into the big and the bulking and the recurring and the scaling up over and over again. This changes completely the business of how do you approach this, how do you analyze it, but also it changes what can you actually use it for. There are certain things that appear here that could never ever appear over there. So in the solid state, we actually want to look at something that is on a huge scale. So not your molecules in themselves, not even the first interactions between the molecules that you can find, not particularly even the first clusters, or when actually in your beaker you will start to see like maybe specks of something. When you actually start to have the material down, so it's maybe the material also of like your table, your computer, something metallic that you saw around when you went to the DIY shop, something big, something that is big enough that you hold it in your hands. It's a scale from which you cannot isolate the atoms anymore, but when you actually look at it, you need to look at its continuous. And the fundamental difference there is that when you look at an organic molecule, for instance fructose that you have over here, knowing the structure is enough. The structure is 6 carbons, 6 oxygen, and 12 hydrogens. If you arrange them properly, you might wonder, okay, which direction does that bond go, but this thing, in whichever way do you analyze it, you derive it, knowing this one is going to be okay for you. It's going to tell you the properties and you're going to be happy with it. Same thing if you go into the small molecule inorganic molecules, which are often complexes with a metal inside. Here you have 1 platinum, 2 chlorides, 2 nitrogen, and 6 hydrogen. This thing is known as cisplatin. It's a notorious anti-cancer drug. Again, you might make a solid out of this if you manage to make it crystallize, but at the end of the day, the thing that you're concerned with is this structure over here. Knowing this one will tell you everything about the interactions that you're looking for, because you're looking for the molecule, you're not looking for the big, like solid version. This molecule, you want it by itself, maybe in a solution, maybe interacting with something else, and like this one, but when you look at the properties, you look at the properties of a molecule. When you find yourself with a solid chemical compound, knowing just what are the components is not going to lead you anywhere. Even if you take something as easy as table salt, if you tell me it's 1 sodium and 1 chloride, A is absolutely not true. B is not going to help you. Like, it's not going to tell you anything about the properties of this solid. You're gonna know that stoichiometrically speaking is 1-to-1 ratio of sodium and chlorine. Is not going to tell you how they are arranged in space, how they will how will they react to stress, for instance? If you hit it, does it break nicely? Is it very hard? Does it conduct electricity? Is it magnetic? Can you actually melt it at a very high temperature? Or does it melt at a very low temperature? Nothing about this mix of compositions, or very little about this just simple formula, will actually tell you something about the mix of properties that come out by the nature of having a series of atoms that need to be considered all at the same time. So when we look at solid state chemistry, we look at anything that emerges from the collective arrangement of atoms, the structure and the properties and anything that comes from it. You must remember that this is not a molecule. When you look at a solid, you're not looking at a molecule, you're looking at something that we might be showcasing like this, but it could be 100, 1,000 times the sequence of these atoms all in the same arrangement, and all of our considerations will be valid. What is not valid is trying to treat this one as if it were this thing. If you tell me, oh, but because the bond between nitrogen and chloride is like this, might be, but it's not the point. And usually if you try to derive solid state considerations from just one atom and the other atom, it's wrong and it's not the right argument. So this is something that we will stress over and over again. It's a solid, it's not a molecule. So when you actually go into, okay, we want to make a solid, but what do we mean with a solid? Two fundamental distinctions actually exist, like broadly speaking, which is between amorphous solids and crystalline solids. A crystalline solid is a crystal because it's ordered in 3 dimensions. So you have a sequential like arrangement of all the same atoms in the right stoichiometric ratios in a certain way in space. They are always like that, always repeating. If I look over here and then I move my gaze and I look over here, I expect to see the same stuff. So I could theoretically reduce the problem by just looking at a tiny piece, but I will know that no matter where I go in the material, even if I have 300,000 of this, if I look from this side and I look on that side, I have 3D order, is nice and arranged. Now 3D order, again, doesn't tell you everything that you might need to know, but fundamentally speaking, there are only a limited amount of unique arrangements that you can have in space for atoms that need to interact with each other. They are not redundant with each other, because this is geometry, so you have only a limited amount of geometries that you can actually keep, and that will keep the idea of this needs to be 3-dimensional in space and stuff like that. The different arrangement of the 3D frameworks are usually called the 14 Bravell lattices. So you can actually go and see in order of decreasing symmetry here. So like from a simple cube, which is incredibly supersymmetric, anywhere you go is the same distance, to something that has all different distances, all different angles, all different everything, which is the triclinic, and with different things maybe inside of the cell, which is called the centering. So when we actually go and look at material, we often refer to them as, oh, this is cubic, this is tetragonal, this is orthorhombic, this is triclinic, because we know what is like the bulk arrangement in space. So you have all the arrangement of your material in those nice geometrical shape. And they go in this order here in decreasing symmetry. We're not going to go into the nitty-gritty in this course, but it is possible that you move from one to another if something is changing in the material, and it's something that you consider depending on what type of arrangement do you want for certain properties, because not every arrangement is compatible with all the properties. So this is truly something that reflects itself on a macroscopic scale. Why? Because it's not just one box, is this box in whichever arrangement it is, repeated forever and ever, ad infinity, plus, minus, all the sides you look, it's always this arrangement repeated, and the properties will follow. The other option that we have is that our material is not this nicely behaved, but it's amorphous. So there are bonds in the solid state, but you lose the 3D order. Your material is 3D disordered. So when you look at this zone over here and this zone over here, you can sort of recognize roughly the environment around which the atoms are bonded with each other, but it's certainly not predictable, not as this one was predictable. Here, if I had looked here and looked here, I would have found exactly the same stuff. Here, similar, but not real. So this doesn't have a shape, you call it amorphous. This type of stuff appears in glasses usually. So glasses lack the crystalline structure of a material, which I know could be a bit disconcerting to hear, because you're like, oh, but it's a crystal, it's shiny, then it's crystalline. Not necessarily. If it's a glass, it's not crystalline, it's amorphous. You can make a glass from a crystal if you force this thing to lose its shape, which is exactly what happened with the very first original glass, which is still a glass from sand. If you burn the sand at very hot temperature and then you cool it down very fast, it will use all the thermal energy to change the shape of these bonds, but then you cool it down so fast that it cannot reshape them where they were supposed to be, and they will block in whichever position they were left, and that will make a glass. That's still a solid. You still have a series of considerations, but they are much more difficult to treat in a standard way, because they lack of this type of standardization. This standardization gives us a lot of power of prediction, of calculation, of understanding. As I said, we're not going to go particularly inside this type of business. If you want more details on actually how do you treat a structure, how do you figure out what's going on in a material, in a crystalline material, you should come to crystallography, which is the advanced course that sort of follows this one, if you want. So now that we discussed the fact that solids are not molecules, we should address what are like the things that can actually go on in solid, which is not necessarily different from what you've seen in previous courses of chemistry, but it's just reframed in a way that makes it a bit more accurate for the business that we have. Because actually solids in their own nature can have a lot of possible bonds type. So ionic bonding, which is the thing that is usually in table salt, sodium chloride, maximizes the electrostatic interactions between the atoms. So that thing is the thing that holds the whole material together. In the whole 3D space, the thing that holds it is trying to maximize the electrostatic interactions. Usually these materials are very high symmetry and very high coordination number, meaning that for every atom that you have in a certain position, you will try to pack as many atoms that optimize those electrostatic forces around it and cluster it and call it a day. On the other hand, you can also have a covalent bond in a solid, but a covalent bond is not trying to maximize how many atoms do you actually cram together interacting with each other. It's trying to maximize something different, which is optimize the directionality. So you don't want as many atoms as possible. You want all the atoms arranged in a very, very specific position, very directional. So these, like starting from here, the other atom that you don't want it here, you don't want it here, you want it going through this line and then through this line and then through this line and then through this line and all over the space, repeating like this. This usually leads to a lower coordination number, but it optimizes the type of arrangement that you have. Then you have the option of having molecular materials, which is often what happens when you made your molecule in solution, you crystallize it, it comes down as a molecular material. So it keeps the arrangement that it used to have in solution, the thing that you might have found with other techniques. And then the interaction between these molecules makes the thing go down as a solid. Now, one option is that you have van der Waals Fulsers. So usually you have strong covalent bond in a layer, for instance, so there is a different level of coordination. But these layers, coordinated and bonded covalently, interact with each other with these weak, like a bit more mobile type of forces. But at the end of the day, you still manage to keep everything interacting, coming down. And then you have the hydrogen bond, which is something that you know from water usually, but when actually is led into the solid state, it's still the same concept, but it also tries to optimize the specific directionality. So it's not as fleeting as what you will expect for water in solution. Once you have a material that is hydrogen bonded, connected in the solid state, it might mean that there is a longer distance between different different clusters here, but it still means that all of the material in the 3D space has this type of interaction, and they are more framed, solid and steady than they used to be in other circumstances. The fact that these type of interactions exist and they don't exist beyond what is a molecule by itself is the thing that allows you to have liquid nitrogen, because if nitrogen had to have no interaction, it could not go into the liquid state and then maybe solidify. And it's also the thing that allows you to have liquid helium, because helium by itself, why would it ever interact in anything that is not a gas? Because of this type of interactions. Once you leave them in the solid state, they are framed and they need to stay there and keep interacting there, possibly in an orientation that is fixed. There are a lot of ways that you can try to systematize these type of bonds, because they appear or not appear, or appear at different degrees depending on what constituents from the periodic table do you have. Inevitably, they come as a reflection of the periodic properties of your material. So here I plotted a nice like 3D periodic table. So you don't only have the periodic table that you're used to with period and group, you also have the electronegativity. So this like amount of like blocks are higher if the electronegativity is higher. Now, the difference in electronegativity in materials that end up being ionically bonded is usually very high. So if you have sodium and chloride, they're at the two different sides of the periodic table. The electronegativity trend goes in that direction. So if they have a huge difference, then they would prefer to be covalently bonded. But on the other hand, if you have a very low difference in electronegativity, then the bond will prefer to be covalent, because they are more nicely arranged that way. But the periodic table is very big and very varied, and there are a lot of intermediate points in which are like, okay, but here, how does it count? And the question of how does it count is the gray area of intermediate behavior. Particularly important is that I know that several of you probably looked at chemistry by looking at this and looking at this. When we go into solid state chemistry, we need to remember that the transition block, the D block, exists, and the lanthanide and actinide block, the F block, exists. So please do not be traumatized if they pop up, and I would advise looking at the periodic table a bit more. So depending on where you pick your atoms, and if your atoms actually make a solid out of whatever interaction do you have, you might have a different spectrum of bonding, and also different like bonding coexisting with each other. So in a solid like lithium sulfate, the sulfate to oxygen bond, which is over here, will be primarily covalent as a type of interaction, but then the interaction between that and lithium, since they are from this side to this other side, will be prevalently ionic. So you can actually coexist in this type of range, which will lead to having stuff like titanium oxide being ionic metallic, and cadmium iodide being primarily ionic covalent, and with the van der Waals interactions added on top to make these molecules interact with each other. And then there is another special type of bond, which is the metallic bond. It's common for something that you will instinctively recognize as a metal, let's say gold, for instance. But it's special for a lot of compounds that you might not think about as a metal that still have a metallic behavior. We're going to discuss it later. And here the concept is that you cannot say, oh, it's this bond, this other bond, this other bond. The electrons are all over the place in all over the material. The metallic bond is in itself something that you have as a characteristic of the solid state. So now that we found ourselves with all this possible range of possible bonds, possible degree of bonding, it's not very handy because you keep saying, okay, but this is partially this is partially that, how much of this, how much of that. It's not exactly the best way to approach things, and it's a very fundamental way, but it's not the most accurate. Because the electrostatic description, in which you keep the electron, I give you the electron, works when you have some very high difference of electronegativity, like in sodium chloride, and it ends up being with a picture like this. When you have a covalent description, usually you can use hybridization and have like this sort of covalent description, but that only really works if you are working with carbon. When you go out of carbon, this thing sort of crumbles down because it's not the best description that you can have. The question that begs here is, can you have something that actually encompasses all bonding types all at the same time and it would just work? That thing is called the molecular orbital theory, which some of you might be acquainted with. Others, this might be your introduction to molecular orbital theory. Now, the idea between molecular orbitals is that you should not look at an atom by itself and the other atom by itself and then try to play Lego and see if they match, but consider that when two atoms will interact with each other, the orbitals will interact with each other, and the result of the interaction between different orbitals from different atoms will account for more than just what they were when they were isolated. So the interaction will lead you to a different final point. So when you have two or more atomic orbitals, you end up with two or more molecular orbitals. So when you have, for instance, two s orbital like this, if you bring them close enough that they are interacting, you should not anymore think about two single atomic orbitals left on their own devices but maybe touching each other, but an interaction that will just make two new different zones for the electrons to be. One in which they can really much interact with each other, which is the bonding part, and one in which they don't really like to interact with each other, which is against the bonding. So the molecular orbital is a discrete energy state that you create between two atoms where you can place the shared electron density. So the interaction between the atomic orbitals will lead you to have a new zone of electron density in which you place the electrons. All the basic rules that you learned in basic chemistry, in which you have the Pauli principle and the hand rule, and you want to occupy as many of them as possible and then possibly start to pair the spins, they still stand. You just place them a bit differently, and then of course depending on the shape of your atomic orbitals, you end up having different shapes of this shared electron density molecular orbital arrangement. The bonding is the molecular orbital with the lower energy, so preferential to start placing the electrons, so the more accessible, the one with the higher electron density. The anti-bonding is the one that gets created as a reflection of the interaction. Higher energy, less access, usually less electron density unless you cannot avoid it. When you treat your atoms with the molecular orbital theory, you can reconstruct any type of bonding. It will just work. It doesn't matter if you were like, oh, but this thing was a bit more ionic, this thing was a bit more covalent. Molecular orbitals will work. So when you want to look of how things interact, how do they scale up, how do you account for the interaction of a lot of atoms at the same time, with possibly unknown level of difference of electronegativity and coordination and stuff like that. You go with molecular orbitals. It's a bit more complex as an approach, but it works because it allows you then to just think about electron densities, more, less, better, worse, fine, but you just think about the bond in terms of electron density. When you want, if you want more context and more theory for this type of business of molecular orbitals, I will advise you to go into this type of link. Now this concludes the first part, and we'll jump into the other video afterwards, in which we talk about distribution of electrons in solid. So see you in the next video.